Hello students, and welcome to topic 9 of alternative and renewable energy sources. The topic we will be covering is solar thermal systems and components. This topic's lecture is broken into two parts. There is an activity with part 1. The activity is recorded and you are to work the activity along with the recording. Solar thermal systems have different applications, much of which depends upon the operating temperature. Here is a demonstration of low temperature application. Hot tubs, swimming pools are a popular application of low temperature solar thermal. In fact, the largest application of solar thermal in the United States is for swimming pools. Medium temperature solar thermal systems are used for domestic hot water and space heating. Solar thermal can also be used for air conditioning. This slide demonstrates a high temperature application. Solar thermal can be used for electric power generation, industrial process heating, or air conditioning. Top left photo, solar thermal, providing domestic hot water and space heating to a residence in Northwest Ohio. Top center photo, solar thermal system, providing domestic hot water and radiant floor heating to a straw bale building in Oberlin College. The radiant floor heating allows students to utilize the building year-round. Top right photo, solar thermal and solar electric system, providing domestic hot water at a low-income housing unit in Columbus. Bottom right photo, solar thermal providing radiant floor heating at a greenhouse in central Ohio. And bottom left photo, solar thermal system providing domestic hot water to a residence in southeast Ohio. The principal applications of solar thermal in the United States are domestic hot water, pool heating, as well as space heating, as stated. Solar thermal has residential applications as well as commercial and agricultural. The residential applications are domestic hot water, pool, swimming pool, and a hot tub, space heating, water purification, and air conditioning. Here are some photos of residential applications. This slide demonstrates the use of solar thermal for a restroom in a park and also demonstrates the installation of solar thermal for pool and spa heating. This demonstrates a large variety of commercial and industrial uses ranging from hotels, laundries, car washes, to industrial process heating. Here is a commercial rooftop application. An apartment or hotel application. A car wash. A hotel application. An industrial food processing application. There are a number of agricultural applications ranging from crop dyeing, greenhouses, dairy processing, meat processing, aquaculture, and food processing. Here's a demonstration of crop drying. Four types of solar thermal systems are shown. Thermal siphon is a type of system that incorporates a water reservoir positioned above the solar thermal collector. This allows for water to circulate through the system by natural convection currents. The drain back system allows for all the fluid to drain back into a reservoir when the pump is turned off. The pressurized indirect system is the most popular type of residential system. The fluid that circulates through the solar collector is isolated from the water being heated. This allows for an antifreeze to be mixed with the solar thermal fluid. The indirect system is always identified by a heat exchanger. The pressurized direct system can be used in climates that are not subject to temperatures below freezing, and also requires the water flowing through the system will not result in mineral deposits. The difference between the direct and indirect systems is the indirect system has a heat exchanger, the coil of pipe in a reservoir, and the direct system heats the water in a reservoir directly as it flows through the solar thermal collector. The thermal siphon system allows for natural convection to circulate the liquid through the collector. This system depends upon temperature stratification in the storage tank. The cold water at the bottom of the tank is heavier and flows into the bottom of the collector. The fluid is heated, becomes less dense, and circulates back to the top of the tank. Further cold water is supplied to the bottom of the tank, and hot water for use is drawn off of the top of the tank. This demonstrates the operation of the drain-back system. When the pump turns on, the fluid is drawn from the drain-back reservoir and flows into the bottom of the collector. The pump must be capable of supplying enough pressure to force the fluid up and through the collector. There is a temperature sensor at the top of the collector and another in the storage tank. When the collector is hotter than the water in the storage tank, the pump turns on. During the nighttime or on cloudy days when the temperature at the top of the collector is not warmer than the water in the storage tank, the pump does not come on. If the temperature in the collector and/or the reservoir becomes too hot, the pump shuts off and the liquid drains back out of the collector. The system also demonstrates the most popular storage tank arrangement. The storage tank, which is heated by the solar thermal collector, supplies preheated water to the standard water heater. Supplies preheated water to the standard water heater. This arrangement allows for times when the solar collector does not heat the water to the desired temperature. The standard water heater will complete the heating. The pressurized indirect is demonstrated. The fluid that goes to the collector is different than the hot water to be used. This allows for antifreeze in the fluid going to the collector. The indirect system is evidenced by the heat exchanger in the storage tank. The pressurized direct system is shown. The water to be heated is heated directly in the solar thermal collector. This type of system can only be used in areas in which temperature does not go below freezing. The additional requirement is that the water does not contain minerals which can deposit in the solar thermal collector. There are different types of solar thermal collectors depending upon the intended use and temperature. The flat plate collectors are used for domestic hot water and space heating. The evacuated tubes has the advantage of supplying water at a higher temperature than a flat plate. The unglazed collectors are relatively inexpensive and are used for heating swimming pools and spas. The integrated collectors have special applications such as the solar thermal system. A closer view of the evacuated tube and the flat plate collector are shown. The relative efficiencies of the different types of solar thermal collectors are shown. The unglazed or pool absorber have a relatively high efficiency when the water temperature and the ambient temperature are close to the same. The flat plate collector has a higher efficiency that extends to a greater temperature difference between the water temperature and the collector and the ambient temperature. The evacuated tube demonstrates the higher efficiency of the collectors for greater temperature differences between the water and the ambient temperature. Some construction details of the flat plate collector is shown. The single or double glazing is meant to protect the inner flow passage tubes and absorber plate from the elements, as well as trapping the thermal energy inside the collector so that outside air currents will not cool off the collector surfaces. This will allow heat to build up. The absorber plate is usually made of copper or another material that has a high thermal absorption and conduction rate. This increases the actual collection area and conducts the thermal energy toward the flow pipes and the fluid. Most collectors are constructed of extruded aluminum for weight purposes. Most installations are on a roof, as well as for their ability to withstand being outside all year long. The insulation type is important to pay attention to when choosing to purchase a particular collector. As with any materials, some are better at doing their job than others. We don't want thermal energy leaking through to the backing and thus being conducted back outside. The collector should always be installed with the inlet manifold on the bottom, which will allow the cold water to utilize the convection principle learned earlier and thus rise through the system while gaining as much thermal energy as possible. If the cold water were to be introduced at the top of the manifold position, it would also be acting upon by gravity, which would cause it not to spend as much time inside the pipe as needed, thus missing out on picking up as much of the available energy as possible. This shows the construction details of the evacuated tube. The vacuum inside the evacuated tube collects greatly increases the amount of thermal energy focused into the pipes. Although they look easily breakable, they are rather durable and capable of withstanding extreme weather conditions. Most evacuated tubes are not made in the United States and therefore not constructed with a high degree of quality, assurance, or consistency. If you are going to purchase these, be prepared to do your homework to find not only the best deal, but the best quality. Reflector material varies amongst manufacturers. A major concern of these is snow buildup. With the flat plate collectors, the snow will slide or be blown off the smooth surface. Evacuated tubes allow snow and leaves to build up in between the tubes and down near the bottom of the members. The unglazed collector is shown. They are uninsulated because the temperature difference between the water in the collector and the ambient temperature is small. These are the most inefficient type of collectors on the market. However, they are inexpensive and work well heating pools. Most incentive programs do not offer funding for unglazed solar collectors. Here is demonstrated the desired properties of the flat plate collector. It needs to be insulated on the back side. Its glazing should allow the solar radiation to be transmitted through easily. The absorber inside the collector should have a high absorptivity and a low emissivity so as not to radiate the energy back into the environment. There are different types of piping arrangements inside the collector. Some collectors have a serpentine piping arrangement which allows the fluid to go through the entire plumbing circuit. This can allow for higher temperatures exiting the collector. The other type of piping arrangement is the manifold. There are multiple pathways for the fluid to go through the collector. By the arrangement of the entrance and exit piping, all pathways have the same length. The absorber plate, which is connected to the piping, is shown. The absorber material and coating must have a high absorptivity and low emissivity. The different types of absorber coatings are shown. Collectors are manufactured with a variety of different absorber surfaces, each recommended for specific climates. The higher the absorptivity of the surface, the greater ability to absorb instant energy. Notice black paint with absorptivity of 0.85, black chrome with absorptivity of 0.95 and blue sputtered with absorptivity of 0.95. The advantage of blue sputtered over black chrome is a higher emissivity value of black chrome, which is a measure of the ability of a material to hold and release heat. Black chrome and blue sputtered are recommended in climates such as Ohio. This demonstrates flat plate solar thermal modules in a snow environment. Flat plate modules have the advantage of melting snow. If they are at a slight incline, the module will begin to heat up and the snow will begin to melt and slide off. Evacuated tube collectors do not have as high a surface temperature due to the absorber being in a vacuum tube. Therefore, evacuated tube collectors do not offer the same advantage as flat plate collectors to melt snow. As stated, the evacuated tube collectors deliver higher temperatures but do not have the same efficiency with respect to gross area due to the empty space between the tubes and the vacuum space between the outer tube and the absorber. Evacuated tubes have the disadvantage of being fragile. There are two types of evacuated tube collectors. There is a heat pipe, shown in the top view. The liquid at the bottom of the inner tube evaporates and goes to the top of the tube and transfers its heat to the solar thermal liquid by condensation. The liquid condensed then returns to the bottom of the inner tube to complete the cycle. The heat pipe evacuated tube must be mounted at an angle. The heat pipe configuration shown in the lower view is known as a direct flow or flooded design. The heat transfer fluid actually flows into and out of the evacuated tube. This type of evacuated tube can be laid flat and still operate. The upper portion of the tube fits into the manifold. As the fluid inside the heat pipe evacuated tube can reach very high temperatures, there is provision to close off the evaporation condensation pathway at a predetermined temperature. A concentrating solar thermal collector is shown. There is no absorber. There is a reflector surface which concentrates the solar on the pipe running through the center. The unglazed collector shown is made of heavy-duty rubber or plastic, which is treated with an ultraviolet light inhibitor. The integrated solar collector and storage is shown. In this case, the absorber is also the storage. There are three important areas with respect to the solar thermal collector. There is the gross area, which would be the area that the collector would take up on a roof. There is the aperture area, which is the area of which the glass, which the sunlight can go through. And finally, there is the absorber area, which is simply the area of the absorber that is attached to the piping. There are different and pictorial. These areas are defined and a pictorial is given here. When the efficiency of a solar thermal module is given, the area from which it was calculated must also be given. This is a perfect example of how the efficiency will change according to which area is being used in the calculation. In this example, the efficiency with respect to the absorber is 79.8%. The efficiency with respect to the aperture is 76.2%. And the efficiency with respect to the gross area is 68.4%. Solar thermal collector efficiencies are most often calculated with respect to the gross area. This demonstrates efficiencies of unglazed flat plate, glazed flat plate, and evacuated tube collectors. The vertical axis on the left is the efficiency. The horizontal axis is the temperature of the fluid entering minus the ambient temperature, the quantity divided by the solar radiation. We will learn how to calculate these efficiencies under different conditions using the Solar Rating and Certification Corporation data sheets. Here we see the upper portion of one of these sheets. It gives us the supplier and address, the model number, the collector type, and the certification number. The table gives us approximate solar collection for different weather conditions. The collector specifications of gross area, the weight, the pressure, the aperture area, and the fluid capacity are also given. This slide gives information about the frame materials used in the collector, absorber coatings, and so forth. The sheet also gives us a straight line equation for the efficiency. The y-intercept in this case is 0.376, and the slope in this case is minus 0.233 BTUs per hour foot squared degree Fahrenheit. If there are any questions, please post them on the eLearn Help discussion.